5 years ago when the first RealSense came out, that was one of the best pieces of hardware that you can use to build robots with, and still alive today, and it keeps getting better and better. So I think that is opening opportunities for people to build intelligent solutions into robots. And we'll chat some about that, and you'll get to hear about RealSense directly from the team. Like we said, my name is Cam Buscarin, part of AWS Robotics and open source teams. I work with our robotics teams to sort of communicate some of the things we're doing in the open source community, building some of our products, and engaging with all the developers. Let me get a show of hand here. Who is familiar with ROS? Who has actually used ROS in the past? A few? Okay, good. So let's dive right in. And I've been lucky to have worked on some great robots, and this is one of them that I've worked a few years ago. And I promise you that not all of them are as useless as this one. But we got a few things I want to chat to you guys today about, and so let's dive right in. We're going to talk about three things today. I'm going to just walk you through what the traditional robot application development looks like for most developers today, and how is the paradigm shifting, being able to leverage the cloud and cloud simulation to sort of speed up the development process. We're going to chat about ROS and ROS 2, and how under the hood that is allowing the developers to use stable APIs and SDKs to sort of just develop their application, focus on their algorithms, and don't have to reinvent the middleware, how it traditionally has been done in robotics for many years. And then we're going to close in with AWS RoboMaker, a service we launched last year to build, test, and deploy robot applications using ROS, and where you can do many things to sort of manage your application deployment, over-the-air update. You can launch simulations at scale. And I'm going to get to the slides. I'm going to go through the slides to see if we get a chance to go hands-on with the AWS console and launch a simulation. So most robotic startups, when they usually start and are building a robot solution, if they're following a good process, they start with what is the customer need. They try to figure out a customer user space where they can build a solution. So after they have identified the customer need, you focus on figuring out what is the exact problem you're trying to solve. And in this particular example I'm going to walk you guys through, we're going to build a spaceship robot application, a Millennium Falcon application. It just made for pretty nice graphics. So what does that look like, right? You first have to design a prototype of your robot. You have to manufacture the components of your robot. You have to develop the firmware that goes into your motor controller boards, your main boards, all the sensors that integrate with the robot. After you have developed the firmware, you have to develop drivers for your robot, and then you can start doing your system software and your operating system. Then you have to start integrating, testing, building your robot framework. And then finally, you can start developing your application and your solution, the problem that you're solving for your customer. So traditionally, this is a very long process, involved process that takes building a robot before you can actually test and prototype a concept or solution. So something that's changing and a paradigm shift in development is that now you can do rapid application development by just getting a bag of software, like ROS packages, using a simulation environment, and then in a matter of hours, you can have a prototype application. Obviously, this is in simulation. It's not the application that would ultimately go to your robot, but you can test your concepts. You can prototype. You can find sort of the sweet spot of your solution. And obviously, your application is not the end-all, be-all, but it has some advantages because you can easily modify it. You can easily extend it, all in simulation without having to spend a long cycle of building a robot. And once you have figured out what the use case that you're building, you can take that specific customer use case solution, you can harden that, build your custom application. You can build your custom component around an ecosystem of open source software, make that more specialized component, which is your intellectual property, and then you can start testing and deploying. Once you have a prototype robot, or you're already manufacturing your hardware system. So some of the advantages, right? It just allows you to test and prototype much faster. And what is under the hood allowing this sort of paradigm shift? Under the hood allowing that is the robot operating system. ROS is the most widely used software framework for robot development, not only for algorithms applications, but also for deployment and prototyping. So ROS was originally developed for R&D development, but because of the robustness and the extensibility of the framework, it has been used extensively in commercial deployments today. So if you look at the ROS versions today, they follow the Ubuntu release. So ROS Kinetic is paired with Ubuntu 16.04. ROS Melodic is paired with Ubuntu 18.04. And next year, Noetic will be the last LTS ROS 1 release, which LTS means is long-term support, which is traditionally 5 years. But then in parallel, there is a development, and we'll get into more details. There is an effort to build ROS with highly production-grade features that can enable the next generation of production-grade robots. And thousands of developers have contributed to this ecosystem. So it's very difficult if to build a proprietary piece of framework that would compete with such extensible framework that developers contribute to today and maintain heavily. So one of the advantages of ROS is that not only it provides the framework, it also has tools that you can use to debug, develop, and prototype your applications. Gazebo is the native simulator in ROS, and it provides you with an interface to plug in different physics engines, different graphics engines, so you can tune and test the fidelity of your simulation. There's a visualization tool that you can use out of the box called Arvis to look at your sensors. Some of the demos that we saw here today with the RealSense use Arvis to sort of visualize the data coming out of the RealSense camera. And then RQT allows you to perform analysis of your data. In this particular case, you're looking at the camera feed from the robot. So who is using ROS today? Well, we know at least this many folks are using it part of the ROS Industrial Consortium, and these are enterprises that are some of AWS largest customers and partners like BMW, Caterpillar, John Deere, and they're extensively using ROS to sort of build solutions around their operations, but also building robots to go to market with. So with that said, that as I mentioned earlier, there is a new initiative to build a next generation of ROS called ROS 2. And one of the paradigm shifts of ROS 2 is that it allows for quality design of the software. There's tools like address sanitizers, thread sanitizers that allow to build a more high quality code base. And along with those capabilities, companies are building solutions that would have a long-term support and long-term cycle. So we at AWS are also contributing heavily to ROS 2. We're vested in the success of ROS 2 because this is what our customers and our partners are using today. So we're contributing on behalf of our customers some of the features that are being leveraged by companies and developers across the ecosystem. So for example, quality of service is something new on ROS 2 that wasn't originally in ROS 1. So if you remember in ROS 1, for publishing topics, you would publish the topic space, the type of message. Well, now in ROS 2, you have the ability to control the quality of the message that you're sending. There are six paradigms there, and how you can tweak and reliably get the messages and control the stream of messages. We're building cross-compilation tools that allows developers to build solutions for ARM-based chips. And another very interesting feature that we're building is this ROS 2 launch sandboxing extension, which is a way that allows your nodes, you containerize your nodes, and you can manage the amount of resources that go to your nodes. So if for example, there is a node that has gone rogue, and there's some software there that is draining your resources, you can make some settings where you isolate that node, and it only has a certain amount of resources that it can take from your hardware. And this has extensively been used in a robotic system threat model that we have published, where robotics companies can leverage our analysis, our threat vector analysis today, to sort of analyze what are some of the key security points that they should harden around their solution. And you can go to this website and take a look at more details of the things we're building there. But we're not the only ones contributing to ROS 2. There's a full technical steering committee working, building adding code to the ecosystem. And one of our main partners there is Intel today. Intel supports the ROS, the next generation navigation stack for ROS. There's a team in Oregon led by Matt Hansen who is porting ROS navigation to ROS 2 and is hardening the code base and contributing heavily to it. So now I'm going to show you guys a quick video of what the ROS 2 navigation stack looks like today. So we believe that there is going to be a great influx of developers wanting to build solutions for robotic products in the future. That's what we have built AWS RoboMaker, and it's in general availability today. And we'll do a live demonstration of what the console looks like. RoboMaker is a service that allows developers to test, build, and deploy robotic applications, and we sort of call it DevOps for robotics. To sort of help you build and deploy your applications. We have 4 main capabilities today that developers can leverage. One, traditionally, to develop ROS applications, maintaining workspace has been a key challenge across multiple developers. So something that we've done, we have a developer environment using our Cloud9 IDE, browser-based IDE, where you can keep your code in the cloud, you can make changes, and you can launch and test your application from there. And we'll get a walkthrough about that. We have also built what we call cloud extensions for ROS, which are native ROS nodes on native ROS API, which connect to other AWS services that you can leverage to stream data and offload compute from your robot. The third main capability is simulation. We host Gazebo Simulation as a service where you can launch and parallelize simulations to test and validate your application. And the fourth capability we provide today is fleet management, which allows you to, over the air, update the software to your robot, maintain version control. You can do conditional deployments where if you only want to update while the robot is charging, or you only want to update while the robot has, let's say 50% or more battery, you can set up these parameters to trigger and update your software. So like I said, the development environment with very little effort, just a few clicks, you can set up a ROS kinetic, melodic, or ROS2 dashing application today, and you can start testing. So you develop your code in the browser, you build the software, you bundle it, and then from there you can launch a simulation. You can check the results of your simulation. If you want to go back and make some changes, you can pause your simulation, make changes, and relaunch your application. Cloud extension for ROS. These are ROS nodes that we have open source where you can add capabilities to your robot like speech recognition using Lex or speech generation using Poly. If you want to get streams of data of your robot, you can use our Kinesis cloud extension for that. If you want to augment the neural network capabilities of your robot, you can offload that to our recognition service. And one of the heavily used one of the cloud extensions that we have a lot of usage for is a CloudWatch integration. So CloudWatch is a CloudWatch integration, and I'll walk you guys through what that looks like. A few years ago, when I was part of a robotics startup, one of the first solutions that we built was a logging system to just log data out of the robots. And there was about 4 or 5 developers who worked extensively on that. Today, this is as easy as just downloading our cloud extension node, configuring a few parameters, and getting the metrics and logs out of your robot directly from our CloudWatch console. And you can build beautiful consoles to sort of visualize the metrics of your robot. One of the customers that has been able to leverage our cloud extension is a company called RoboMaker Systems, and they have a product called Leah, which is a helper walker, which patients use it today during their recovery process. And because Leah has a lot of sensors but low compute, they're not able to process all the data on the robot. So they have been able to leverage RoboMaker and the cloud extension nodes to analyze walking gait of the patients to sort of help the patients in their recovery process. They have been able to enhance the interactivity of the walker using some of our speech generation and analysis tools. So like I mentioned earlier, the CloudWatch extension node, you can use it today. You can log data even if you're not connected to the Wi-Fi or you're not connected to the network. You can log the data to the robot as an offline feature that we provide. You log the data, and once the robot connects to the cloud, then it starts uploading the logs. And we have written a really good blog post about how to use this ROS node. So if you go to this website, you can take a look at sort of how it walks you through how to set it up, how to start using it. So simulation. Simulation is one of the services that we have customers using extensively today. And this feature allows you to you can either bring your Gazebo worlds into our simulation environment, or you can use some of the pre-simulation worlds that we have made. And one of the demos that I'll give you is in a small house world that we have created. There's zero infrastructure to provision, configure, and manage. And you can run multiple simulations in parallel. So you can randomize sort of your environment. You can configure scenarios that you want to test against your simulation. And then you can scale it. You can launch thousands of simulation jobs in parallel with parameter changed, and you can validate your application. And the last capability that we provide today is the fleet management fleet management over-the-air update capability for your robots. Is you basically, all you have to do is install an IoT daemon on your robot. You get the certificates from our console, and then you have end-to-end encryption between the robot and our cloud. And from the console, you can manage an application deployment. So I'm going to give you guys a quick demo of launching a simulation job on AWS RoboMaker. So here's what the console looks like. You have a development environment, you have simulation jobs, and you have fleet management. So in development, if I want to create a new environment, I just click here, and I can pick the version of ROS that I want to use, whether it's kinetic, melodic, or dashing today, to sort of build my application. You pick the amount of resources that you want to use for this instance. But in my case, I'm going to launch a previous environment that I have already created. And this is a TurtleBot robot, sort of like the kit that we have demoed, Intel has demoed here today. So now this is configuring and launching my developer environment, and it's picking the instance that I have previously created. Let's make sure I'm still connected to the Wi-Fi. Yep. So any questions so far? Happy to take any questions now. Okay, so let's walk through this demo. So basically, this is my developer environment. Let me make this bigger. Can you see there? So look, okay. So I have my robot application workspace, which is the ultimate software that goes to the robot. This is the workspace for the robot, and I have the simulation workspace. Here I have, for example, the simulation assets, like the world that we're going to see. In this particular sample that I'm going to show you, we have a simple node that publishes a command velocity twist message, and it just makes the robot rotate at about 0.5 radians per second. And because I've already built this, I'm just going to launch the simulation job. So from here, I can launch the simulation job. And what we'll do is we'll come back, we'll change the turn speed, we'll make it faster, and then we'll go back and look at the simulation job of the robot running, turning a bit faster. So now it has uploaded the bundle to the virtual machine, and it's going to kick off our simulation job that we'll see in a few minutes. So the simulation job has been created, so I can go back to the console and look at my simulation jobs. So now it's preparing the simulation job that we have just initiated. And these are previous simulations that I've run with different robots in different environments. We have a Mars rover demo that I was running earlier, and then we have a TurtleBot that I was running shortly before this. So now, as it's preparing the simulation, what we'll get to see is it automatically has a Gazebo instance, an Arbis instance, an RQT instance, and a terminal. So then from there, I can launch all the visualization tools, I can probe them, and I can use them simultaneously. And this takes about a minute or so to launch the simulation. So once it's ready, the status would change from preparing to running. Any questions so far? Happy to take any questions in the meantime. Yeah.
So say I have a robot that I how difficult is it to import all of my information about my robot and be able to simulate it?
So if you already have your URDF model of your robot in a repo, you can just clone the repo into this instance. For example, here you have a console. So I have this environment where I can just git clone whatever code you have already built. So in this particular case, I already have the URDF, the robot description model for this robot. I just import it from my repo, and I can launch it here. So it's a matter of if you have to create a custom URDF for your robot, then you would have to provision that and create the meshes. But if you already have it, you can import it into RoboMaker and launch it natively. So now the simulation is running. We'll take a look. So the console here shows you how the resources in the virtual machines are being used. And here I can see the Gazebo application, the RVIS, the RQT. So we're going to launch the simulator and take a look. So here I have the robot running. And as you see, it's turning at about 0.5 radians per second. So what we can do is we can go back to the code, and this will take a few more minutes. Let's see how we're doing on time. I think we got a few more minutes. So we can change it to, let's say, 5 radians per second. I can save the code. I'm going to stop the simulation. Oh, I can actually, let's keep that one running, and then we can take a look at this one versus running faster. And this may be a little fast. Let's change it to 4. So 4 radians per second. I can build the application here. So now it builds the code directly on the virtual machine. Is build the code. I can bundle it. And bundle just packages the code in a tar file that then it can be picked up by the virtual machine that runs the simulator. And this usually takes a few more minutes. Just creating the bundle. It's done. So now we can go ahead and launch our simulation. So launch simulation. It's telling me that I already have a job running. Do I want to run them in parallel? Yes, sure. So now it's provisioning a second simulation job. And it'll tell me as soon as it's done. And then we can go back to the console and take a look at the robot turning at a different speed. Any questions so far? Any thoughts, concerns? Okay, so now it has created a simulation job. So I can go back to the console, look at my simulation jobs. It's preparing the second simulation. So as we saw earlier, this is the first simulation. And this world particularly is open source. We have completely open source this world. So you can pull this from our repo and start playing with it. We have additionally a library world, which is the videos that I show in the PowerPoints. And we also have a racetrack. So if you want to train a RC car to run around a racetrack, you can do that as well. So let's go back here. Still preparing the simulation. And I will show you what those worlds look like in the meantime. So GitHub, github.com/AWS Robotics. This is a different one. So you can find our environments here, and I would look for, so this is the racetrack world. We'll take a look at that. So you can play with this Gazebo world today. You can just pull it from our repos and train we have a sample application to train a reinforcement learning agent on this track, and you can race in it. So let's take a look. Still preparing.
I have one question.
Yep.
That seems very interesting if I want to run extensive simulations and I'm interested in the fidelity of the simulator. For example, what sensors, what sensor models it can simulate. If you have any additional plugins, for example, to simulate sensors.
So these are the native Gazebo sensor models. So from there you can extend. Gazebo has an API to extend sensor models. You can use the standard sensor models today with the fidelity that they provide, or you can extend it using the Gazebo API and bring in a plugin for that. So it's how you would natively do it in Gazebo, you can import it into our simulator. So let's take a look. So now our second application is running. We can take a look. We go down, launch the simulator. So now we see that this robot is running faster. So this is the first simulation. And this is the second simulation where we changed the turning speed of the robot. Yeah, so just wanted to give you guys a quick demo. If you want to figure out how to run this through yourself, we actually have a self-guided tutorial. You can go to RoboMakerWorkshops.com, and we have a pretty well guided instructions built by our solution architects, which you can just use yourself. And there's about 5 applications you build there using different simulation tools. And it also walks you through how to deploy to a real robot. If you have a turtlebot or you have a robot with a RealSense, you can deploy directly to that application. So something that we are partnering heavily with is with universities, and we have an academic program where we have a education arm at AWS called AWS Educate, where students can have a classroom in a AWS console just for education. And there's a number of applications number of universities that we have partnered with, like University of Central Florida, Cal Poly, where they're using RoboMaker today in the classroom. Something fun that we did this weekend, we actually sponsored a hackathon at Arizona State University where they tested, built, and deployed an application for a small robot to race around a track. And there's some folks here in the audience that were part of this. So these are very interesting tools today that are available for students that weren't available, let's say, 10 years ago. So they're getting advantage of the barrier to entry being lower. So like I said today, you can try it today. Our Cloud9 IDE simplifies the ROS development environments. You can use our cloud extensions to add extra capabilities to your robots. You can use our simulation to accelerate the robot development and validation. You can use our fleet management to update your robot. And this is available. You can test it yourself today. We have a free tier that you can use. It gives you about $20 to $25, and RoboMaker, the only cost is simulation hours. We only charge per simulation hours. Any other AWS services that you have is their own tier pricing. With that said, thank you so much. Happy to take any questions.
All right, well, let's thank
Thank
Dan
you.
for the great talk.
Thank you.